Hi everybody and welcome back. We are going to be talking about exponential functions in these set of videos. So first we need to define what an exponential function is. It's basically, exponential function is just basically a number raised to different powers of x. Now notice that these powers of x can be any real number. So we can define things like 2 raised to the square root of 2 power, which we don't know how to evaluate directly, and in fact it takes a little bit of calculus to do that. So we're not going to talk about how to evaluate weird stuff like that, but notice that these are just powers, so we can actually plot them just using the integer values. So the 0th power to the 1st power to the -1th power, etc. There is one restriction on these functions. B has to be positive, B cannot be 1. B cannot be 1 is easy enough to figure out, because if we let f of x be 1 raised to the x power, well, 1 raised to any power is 1. And so this is actually a constant function, not an exponential function. Because exponential functions have certain shapes to them, and, well, this constant function does not have that same shape, so we must throw that case out. But otherwise, any positive number other than 1 works for the base. This constant b is known as the base of the exponential function, and notice it is a constant, not a variable. So notice that the variable here appears in the exponent, not in the base. Other properties, we're always going to be greater than or equal to 0. Continuous will always pass through the point 0, 1, because b to the 0 always equals 1. So that's f of 0. We'll always have a horizontal asymptote on the x-axis. If b is greater than 1, we will be increasing. If b is less than between 0 and 1, it's decreasing. And then these functions are always 1 to 1. So, I really want to talk about these graphs. To plot these, you just plot the powers of the integer values. That's not very hard, so I'll leave you to read that in the book. But you actually should really know the general shape of these graphs. So let's look at f of x equals b to the x, where b is greater than 0. So notice, or not greater than 0, greater than 1. So the graph of these functions always look like this. They're always going to start very low near this x-axis, and then they're just going to suddenly spike up. And they're going to always pass through this point 0, 1. So notice we do have our horizontal asymptote here on the x-axis, and you really should know in particular the end behavior here. Notice that the end behavior as x goes to positive infinity means that f of x will go to positive infinity, but as x goes to negative infinity, f of x will go to 0. So this is of a particular interest when we go into calculus, so this is something you should have learned now to save yourself trouble down the road. Let's look at a related function, though. Let's look at f of x is equal to b to the negative x. Now, this function looks like this, and b is going to be greater than 0 again. And then we're going to have 0, 1 here. And you may be saying, well, wait a tick. Didn't you just say if b is greater than 1, which is what I should have wrote here, I should be always increasing. But this graph is clearly always decreasing. Well, look at b to the negative x. That is just b to the -1 raised to the x power, which is 1 over b raised to the x power. And if b is greater than 1, then by taking reciprocals, 1 over b is less than 1, and in fact it's also greater than 0. So notice that this doesn't violate my increasing, decreasing conditions at all, and functions are frequently written in this form versus writing them in fractional form, so you need to be aware of that fact. Again, the end behavior in particular is of importance, so we need to know that as x goes to infinity, the functional values will go to 0. And as x goes to negative infinity, the functional values go to positive infinity here. And again, we also have our horizontal asymptote on the x-axis as well, which the computer doesn't want to give me my pen, so there we go. There we go. Two more graphs to talk about here, so let's flip back. So let's talk about now what happens when b is less than 0. So if we look at f of x equals b to the x, when b is between 0 and 1, we just basically get the graph I just drew. We get something that looks like this. Goes through 0, 1. Has an asymptote on the x-axis. And it has n behaviors. As x goes to infinity, f of x goes to 0. And as x goes to negative infinity, f of x will go to positive infinity. So, this is another pattern you should know. In particular, again, the biggest thing besides always going through 0, 1 is the n behavior here. And then, last example here, this one would be f of x equals b to the negative x, where b is between 0 and 1. And this graph looks like a normal exponential function. 0, 1. Asymptote here on the x-axis. And again, note that if we work with this inequality, for example, if b is less than 1, then taking reciprocal says that 1 over b is greater than 1, and this function is really 1 over b to the x. So, that's why it looks like the normal exponential function. And we have x goes to infinity means that f of x also goes to infinity, and when when x gets really small, f of x tends to 0. So again, the big thing is learn the n behaviors. So notice that when I zoom out, I had 4 different patterns. Basically, it depends on what the base is, if it's greater than 1 or between 0 and 1, and whether you're raising it to the x power or to the negative x power. And if you know these 4 basic functions, these 4 basic patterns, that will make your beginning classes in calculus a lot nicer when you start studying things called limits. So, that's all I'm going to talk about now. In the next video, we'll talk about how to graph specific function and its translation. So see you then.